All right, let's go ahead and get started. I do want to welcome you to this second installment of Unit 16. This is Reaction Kinetics. If you're following along with me in the zoomed all text, this is 12.2 Rate Laws and Introduction. So last time we were looking at this reaction. We have 2 moles of NO2 gas yields 2 moles of nitric oxide gas plus oxygen gas. And before we proceed, I want to do a little bit in the way of review. I want to talk about the factors that would in fact affect the rate of the reaction, this reaction or any other reaction. The first one would be temperature. So how would temperature increase the reaction rate? Well, if we consider this reaction, we can imagine that if we increase the temperature, we increase the kinetic energy of these particles, the NO2 particles, right? So if we increase the reaction, the temperature, we increase the kinetic energy, which in turn is going to increase the rate of the reaction. If there's more collisions, there are going to be more effective collisions. If there are more effective collisions, there's going to be a greater rate or faster rate. So temperature certainly is going to affect the reaction rate. In fact, there's a rule of thumb you can use that for every 10-degree increase, there is a doubling of reaction rate. For every 10-degree increase, a doubling of reaction rate. So that's the first one. The second one is concentration. How might concentration then increase the rate of the reaction? Well, you can imagine that if there's just more NO2 particles to collide into one another, there's going to be a faster reaction rate, and that's exactly correct. That's what happens. If you increase the concentration, you increase the reaction rate. Now, here's something that's interesting, and that is if you lower the volume, if you decrease the volume, you effectively increase the concentration. Now, how does that happen? Well, think about it. If you push the particles closer together by decreasing the volume, you have in effect increased the concentration. They're in closer proximity. They're going to bang into each other more frequently. So concentration also affects reaction rate. And the last one we want to talk about is catalysts. And we'll just mention it here. We'll talk a lot more in detail about catalysts later. They create an alternate pathway for the reaction by lowering the energy of activation. But they also effectively increase the reaction rate. So there you have it. Temperature, concentration, and catalyst. 3 things that increase the rate of the reaction. All right. So now let's move on. So we said that we were considering this reaction. We had got 2 NO2 gas yielding 2 NO gas plus O2 gas. Now, the important thing that we need to keep in mind is this. When we're discussing reaction kinetics, there is a reverse reaction that is occurring. In this case, it would be O2 gas plus NO gas, or 2 NO gas, yields NO2 gas. The problem with the reverse reaction is that it complicates the reaction kinetics picture enormously. Because now, if you have a forward reaction operating simultaneously with a backward reaction, then both the forward and the backward reaction theoretically are affecting the reaction kinetics. And that makes things very, very complicated. So what we're going to do is we're going to look only at the reaction in the forward direction. We only want to consider the forward direction, and we'll only study the reaction when the reverse reaction is unimportant. So we'll look only at the forward reaction, and we will simply, for our purposes, ignore the reverse reaction for our purposes of study. Okay? So we'll keep that in mind. Now, in our last video, we talked about different types of rate laws, right? And one was called the differential rate law, and this is the one that I want to look at now. The differential rate law for this reaction is this. It's rate, and rate is always in the unit concentration per unit time. So we're either gaining or losing, usually losing some amount of product over time. So it's concentration over time. So we generally say it's moles per liter per second, right? And I say per second because generally these are fairly quick processes, and so seconds is a good way to talk about them as opposed to say hours or days or some other time period, right? So moles per liter per second would be the rate unit, right? Is equal to K. Now, this is not the same K that we saw when we discussed equilibrium. It's a different rate. It's a different K. It's called a rate constant, and it carries its own unit, and the unit changes. It's going to depend on other factors that we'll talk about later, times the concentration of the reactant. Now let's talk a little bit about this reaction right here. Notice the reactant in this case was NO2. So NO2 will go in the brackets. The brackets indicate concentration. So we have concentration of NO2 to some power. We call that the reaction order. To some power, we call the reaction order. And it's usually a small, low integer, something like 0, 1, or 2, or maybe even 3. No more than 3. 0, 1, 2, or 3. Now, the next thing I do want to tell you, though, is this. You cannot, unlike when we looked at the K for equilibriums, you cannot look at the coefficient. You can't look at the coefficient in front of the reactant in this case and say, well, that's going to be the power to which I raise this concentration. It just doesn't work that way with reaction kinetics. You have to use empirical data. You have to use experimental data in order to determine what that N is. So that's very important that we remember. You just don't look at the balanced reaction and pull from the balanced reaction the coefficient like you did with when you were making your equilibrium constant. You can't just look at that coefficient and determine from the coefficient what the order is going to be. So that's it. Rate is equal to K times the concentration of NO2. In this case, that's the reactant to some power. Now, I do want to tell you, first of all, that the rate constant is temperature dependent. So whatever the temperature you're at, that rate constant will apply. If you change the temperature, you change the rate constant, okay? So that's it. That's called the differential rate law. One last thing, and that is this. In this particular case, we had only one product. We had NO2 as a reactant, I'm sorry. We had only one reactant, that was the NO2, and therefore we have only one reactant showing up in the differential rate law. Keep in mind that if you have more than one, and we'll certainly look at examples of those, if you have more than one reactant, you're going to have more than one reactant showing up or concentration showing up in the rate law. All right, so that's that. All right, let's move on. The next thing is this. How do we determine the concentration? How do we determine how much we've got? Well, we'll take a look in a lot greater detail in our laboratory, but we're going to study something called Beer's law. And Beer's law is a law that allows us to convert spectroscopic data, because generally there's going to be a color change. So as the rate, as the reaction proceeds, there's going to be a color change from reactant to product. But our eyes can't see exactly what that color change is. So we use instruments called spectroscopic methods to help us to determine what the color changes are, and then to convert those to concentrations for us. So we'll talk a lot more about Beer's law as time goes on and we do our laboratory. So number one says the concentration of the products does not appear in the rate law because the reaction rate is being studied under conditions where the reverse reaction does not contribute to the overall rate. All right, so again, we don't concern ourselves in the rate law with the reverse reaction. Remember, the reverse reaction is occurring, but it's occurring either at a period of time when it's not important, right? Or we just ignore it altogether. So in the rate law then, or the differential rate law, we don't see products showing up, we see only reactants. In this case, it was NO2. So that was the first one. Number two, the value of the exponent n must be determined by experiment, okay? Only empirical data will get that information to you. It cannot be written from the balanced equation. So when we write the differential rate law, and this is it right here, this is the differential rate law on the right-hand side, K is equal to NO2 to the n power. That n right there can only be determined experimentally. So we'll keep that in mind. All right, the next one is this. So the differential rate law, or just the rate law, describes the relationship between the concentration of the reactants and the reaction rate, all right? So now, once we know the rate law, right? Once we know the rate law, we can determine the rate for that reaction for any concentration of, in this case, NO2, right? So if you tell me the concentration of NO2, I can tell you what the rate is going to be without doing the actual experiment. Next, the differential rate law is related to something called the integrated rate law. We'll talk a lot more about that in the next section, which describes how the concentration of reactions depend on time, right? So again, two different ways, integrated rate law and something called the differential rate law, right? The differential rate law that depends on time. Once we have determined the differential rate law for a specific reaction, we know that there is a corresponding integrated rate law and vice versa. All right, so I know it's difficult for you to conceptualize what the integrated rate law is since you haven't seen one yet. You'll see it in the next section, but I just want to prepare you for that next section where we talk about integrated rate laws. So there's differential rate laws and there's integrated rate laws, okay? How do we determine which general type of rate law to determine? It's largely a matter of convenience. What type of information are we being given, right? Are we being given initial rates, or are we being given, say, time and concentration data? So that's going to determine the type of rate law that we're going to use. This will be much more clear in the next section. All right, and the final thing is this. Knowing the rate law for a reaction is important, mainly because we can usually infer individual steps involved in the reaction from the specific form of the rate law. Folks, every reaction involves what's called a reaction mechanism. In other words, when we look at this reaction that we started out with, right? The reaction is not going to proceed in one step. It's going to proceed in multiple steps, and we call that the reaction mechanism, right? The reaction mechanism. It's a series of steps. Generally, one of those steps is going to be slow. In this case, I've said step one is the slow step. It could have been any of the steps. It's the slow step. But one of the major reasons that we want a rate law, we want to determine the rate law, it's because it's going to give us tremendous insight into what the reaction mechanism might be, right? How exactly does this reaction occur? What is the series of steps that must happen in order for this reaction to occur? We're going to be looking, again, a lot more in subsequent sections into reaction mechanisms. All right, that'll do it for this one. I'll see you in the next one. Thanks. Bye-bye.